Okay, so in the remaining time, we're going to talk about assembly programming. This is going to be fun, but it's going to be also relatively easy, hopefully. And I'm going to leave you with a lot of things that you can study on your own. And you're going to do this in your labs, especially the later labs, let's say, so that you can test your programs, you can run your programs, etc. And we're going to look at LC3 and MIPS assembly. And they're essentially very similar, as you have seen so far, with some idiosyncrasies in terms of the differences in instructions. And these are the same readings that we discussed. So basically, we're going to look at some programming constructs, talk about debugging a little bit, more about principles than actually real detailed examples, because detailed examples are actually quite too detailed to cover in even one lecture, actually. But you can study the examples on your own, certainly. We're going to talk about conditional statements and loops that are important, and then arrays. And if you have time, we're going to talk about function calls. If not, you can study them on your own, but they're no different from function calls in any other ISAs, if you will. So remember, we're still talking about the von Neumann model, von Neumann machine, and instruction cycle. These are things that you should keep in the back of your mind. We're going to build our first LC3 program by using conditional branches for looping, essentially. And this essentially, we want to write a very simple program that has 12 integers. And these integers are stored in addresses hex 3100 to hex 31 OB. And usually the way you go about solving a problem remember, we're solving problems in computers, and the first step is really translating the problem to an algorithm, right? And essentially, to do that, we actually create a flowchart of the algorithm. In this case, the flowchart or the algorithm is very low level, as you can see, because we're going to write a program in assembly later on. So basically, you can see that we even decided the register assignments. So we're going to put the address of the first integer in 3100 over here. We're going to put the counter in R3, and then we're going to put the number of integers in R2 over here. So R1 is the initial address of integers, as you can see. R3 will store the final result of the addition, and R2 is the number of integers left to be added, right, at this point. So this is the initialization part. Almost always algorithms have initialization parts, and that's what we're going to do over here. And then the first step is to test whether R2 is equal to 0, meaning whether we have any integers left to be added. If it's not equal to 0, then we do the addition. If it is equal to 0, which means that we've reached the end of all the integers to process, then we actually get out of the loop and do whatever else, maybe output this to a screen, for example, right? Okay, so basically, are we done with all integers? That's what this is checking. If we're not done, we load the first integer into a register. Remember that R1 specifies the address, and that's doing the loading. And then we essentially accumulate the integer value in R3, increment the count, or increment the address, and decrement the count of integers, basically. And that's what it is. And then you basically keep looping, okay? So hopefully this is very similar and simple, and you've already written some programs in your life, in DTH for sure. But if you're taking this course as the first course, then this may be your first program to actually write. But that's not true at ETH. So basically, the next step is translating all of these to instructions in the ISA. And that's what this does. This directly goes into machine code, of course. And we use conditional branches to create a loop. And these are the instructions, as you can see. So you can see that there's a load effective address that loads a value into 3100. And this is basically what we do in the instructions. So this is the load address, as you can see over here. And then we reset the registers, the top two things over here, R3 and R2. And then we initialize the counter, as you can see over here, R2. And then we basically check the condition that's over here. And then we jump out if the condition is true. If not, then basically we execute this block over here, load the value in integers, and then accumulate it, and then increment the address. You can see that different form of adds are used, add register and add immediate over here. And then decrement the counter of integers, increment the address, we go to the next address in the next iteration. And then unconditionally branch, NZP is unconditional branch, unconditionally branch back to loading the value, right? That's what we're doing over here. Or checking the condition, sorry, not loading the value, because we need to check the condition first, because that's our loop exit place. So basically, you need to get the branches right? That's the key point over here. If you're doing assembly programming, you should not branch to here. You should branch to 3004 over here. Okay, so hopefully that's clear, right? And you know actually exactly how to execute all of these instructions in the LC3 data path that I showed you earlier. I'm not going to go through this in detail again, But everything that we have seen in the previous program, you've already seen in the execution of the LC3 data path. I see a hand raised. Is there a question? I see a hand raised by Alexander. Okay, maybe it was a mistake. That's also fine. If there's no question, then I will move on. Okay. Okay, so basically that was our first program, and you know exactly how to execute every single instruction in that program. Now let's raise the abstraction level a little bit and talk about programming, because based on everything we have seen right now, now we know exactly how instructions execute. We're going to show you more of that later the next week. Now you know actually how to build programs that can execute on a real machine, and you know how the real machine is built based on the combinational and logic structure. So nothing is magic at this point. Nothing really should be magic at this point in terms of how you can go from a transistor all the way to assembly programming. And now we're going to close the gap for assembly programming. So we're going to talk about programming now from the high level. So you have a task, and programming requires dividing a task, in other words, a unit of work, into smaller units of work. So it's all of the programming is really divide and conquer in the end. And the goal is to replace the units of work with programming constructs that represent that part of the task that you're subtask, let's say. And there are three basic programming constructs: sequential construct, conditional construct, and iterative construct. And our instructions are actually enabling these constructs, instructions in the ISA. So sequential construct is kind of obvious. You have a task to be decomposed, and you can break it down into subtasks, one following the other. So basically, you break it out into two subtasks so that you can think about the program in an easier way, let's say, or algorithm. Okay, so hopefully that's obvious. Conditional construct is essentially enables you to do one of the subtasks, but not both. So it basically enables you to test a condition, and based on the condition, execute one task. And if the condition is not true, execute some other thing, right? And clearly, this is an if and else contrast, right? Either subtask maybe do nothing. After the correct subtask is completed, the program moves onward, if you will. So you can implement if-else statements or switch case statements, as we have seen earlier. And Verilog also implements these, as you remember. So iterative construct is used to, if the task consists of doing a subtask a number of times, but only as long as some condition is true. So this is used to implement loops, as you can imagine. First, you basically test a condition. If it's false, you don't do it. If the condition is true, then you do the top task. It could be the other way all around also. You could actually test the exit condition also. And if the condition is true, you could exit the loop as well, right? So basically, it's a looping construct, let's say. And if the condition is still true, you keep doing the subtask. For loop, while loop, do while loop are examples of loops. So let's take a look at these constructs in an example program. I'm not going to go through this program in detail, actually, because we don't have time, and it's, I think, trivial to go through it, if you will. So the example program is going to count the number of occurrences in a character in a text file. It's going to use all of the constructs, sequential, conditional, and iterative. And we will see how to write conditional and iterative constructs using conditional branches. So counting occurrence of a character, basically, we want to write a program that counts the occurrence of a character in a file. So we're going to get the character to search from the keyboard using a trap instruction. That's going to be the novelty we will learn at the end of this, but we're not going to go into how it's implemented and the detail of it. So we're going to interact with the keyboard over here. And the file will finish with the character end of text, EOT. This is a special character called a sentinel character. If you didn't know about the word sentinel, it designates the end of something, essentially. In this example, EOT is set to 4, for example. It could be something else. Output result will be placed onto the monitor using another trap instruction, essentially. Again, you will see that soon. But this is how I break my program into the constructs, the sequential, conditional, and iterative. Again, I'm not going to go through this in detail, but you need to initialize the count. And you remember the constructs as pictures over here. You need to initialize the count, initialize the pointer, get the input character from keyboard, get the character from file that we're going to compare to the input character. And then if the character that we got from the file is not end of text, then we keep looping. What do we do if we loop? We check if the end of file. If it's not the end of the file, we check if there's a match. If there's a match, we increment the counter of the characters that match the input character. If there's not a match, we don't increment. And then we get another character from the file and then increment the pointers and the initial address, as you can see over here. And then we keep doing the same thing until the character we read from the file is end of text, right? So that's the iterative construct. And I've already described all of these actually. And then if at the end we prepare the output, we exited the loop, we're done with the file, and we prepare the output to write. Don't worry about exactly what this means. This basically converts the output to an ASCII character that can be displayed by the monitor. And then we output to the monitor, and the monitor displays the character in its own format. Okay. And then we halt the program using another trap instruction to stop the program because we're done, essentially. So this is a full program. And you can read again the Pat and Patel chapter that houses this program. So trap instruction, basically, let's talk about trap instruction because it's important. This is the operating system hardware interface, essentially, in LC3. MIPS has its own instructions. It invokes a service call, essentially, operating system service call. In assembly, it looks like this. In machine code, it looks like this. It's very simple, basically. And you have a trap vector, basically. The opcode is 1111. And trap vector specifies what you ask the operating system to do. So for example, if you say trap vector 23, you basically ask the operating system to get a character from the keyboard, right? Or if you use trap 21, you ask the operating system to output a character to the monitor. If you use trap 25, you ask the operating system, I'm done with the program, halt the program, finish the program, basically. So we're not going to go into how this is implemented. If you're really interested, you should really read the appropriate chapter, input, output, for example, from Pat and Patel, but we don't have time in this semester to really go into it. In systems programming, you will go into it more, but maybe in another version of this course, we can go into it, but not this version. So this is the program that we wrote, and this also in our Pat and Patel book, that basically implements the constructs that we showed you earlier, that basically implements this flowchart. And again, I'm not going to go through this in detail. You can convince yourself that the program does what it does. But again, we don't have time to go through the detail. You can see that we use conditional branch instructions to create loops and if statements. And you can do reverse engineering to identify conditional constructs and iterative constructs like what I show you over here. But again, we don't have time to go through this in detail. Again, nothing is hard over here. It's just translating the program into assembly language and then the machine code later on. You can also start from the machine code and reverse engineer the program as well, right? And you can see that there's a starting address of the file over here. So file actually is stored in memory. In this case, it's a memory mapped file. But again, we're not going to go into that in this course. So let's talk about debugging, because it's going to be something important that you do in all your programming, including your Verilog programming. And this is the process of removing errors in programs. It consists of tracing the program, keeping track of the sequence of instructions that have been executed and the results produced by each instruction. It's clearly a useful technique, right? And one way of making it even more useful is to partition the program into parts like modules and examine the results computed in each module separately. So high-level language debuggers can help you clearly. There are many, many examples of this that I'm not going to go into. Machine code debugging provides you elementary interactive debugging operations. So let's take a look at interactive debugging operations. When debugging interactively, it's really important for you to be able to put some values into memory and registers. You're at a very low level as an assembly programmer, right? You need to be able to test the execution of a part of a program in isolation, maybe one instruction, right? Execute instruction sequence in a program by using the run command. So if you have a debugger that supports this, you can run instruction by instruction, right? And a run command executes until halt instruction or until a breakpoint. So you can step n command, basically you can execute a fixed number of instructions. You could step 1, for example, you could execute every instruction one by one, examine the results and see what you expect, if what you expect is in the registers and memory. And you can stop the execution when desired in debugging clearly, right? You can do that by setting a breakpoint command, by stopping execution at a specific instruction. You set a breakpoint at a particular point where you want to examine the memory and register values. And after this, you can examine what's in memory and registers at any point in the program if you have this infrastructure. That way you can step through the program. So this is very useful clearly. And doing this in Verilog is also very useful, except Verilog is very inherently parallel, right? Assembly, because of the von Neumann model, we execute one instruction at a time, right? So you can actually say, I'm going to execute one instruction at a time. And then you can see what the result of that instruction is. And if what you expect at the high level as a programmer is satisfied, right? So for example, we have a multiply operation in LC3. A program is necessary to multiply since LC3 does not have a multiply instruction. And the following program multiplies values R5, R4, and R5, basically. And again, initially R4 is 10, R5 is 3. I'm not going to go through it in detail, but the program produces 40. The question is what went wrong? And you can examine it by yourself. And to do so, it's useful to annotate each instruction. So again, you have, if you're given the machine code, you can easily annotate these instructions and say, these are the instructions that I have. And if you examine the instruction and the contents of the registers after the execution of each instruction, you may find out that the correct result is here after 3 iterations. But after some point, branch is taken. And the branch should not be taken if R5 is equal to 0, because then you would be multiplying things by more than once. So if you go over here, R4 is 10, R5 is 3, and the program produces 40. Clearly, program should produce 30. The program iterated once more in the loop, basically one too many times. Because the branch condition codes were set wrong, the conditional branch should only be taken if R5 is positive. So basically, we did a mistake over here in the program. We set the Z bit, whereas we shouldn't be setting the Z bit. We should not be checking the 0 condition over here, because that is a boundary condition in which the program leads to one more iteration, which it should not execute, right? So the correct instruction should have been BRP as opposed to BRZP, right? So you can actually find the problems by executing the debugging the program by executing instruction by instruction clearly, or by setting breakpoints. I'm not going to go into the details clearly. So you can do easier debugging with breakpoints. As we said previously, we examined the instruction by instruction, but you can actually set a breakpoint at the branch and see where the branch goes. And you can examine the results of each iteration of the loop, as opposed to examining the results of every single instruction in the loop. And this way, you can actually look at interesting things that you care about, and you can still find the problem, basically. Okay, so does this program work if the initial value of R5 is 0 is another question, and I'll let you answer that. Basically, that's another corner case. Basically, if R5 starts with 0, does this program still work? And the answer is no, this program doesn't work. Basically, that's a problem. So basically, you should test the condition. You should test whether R5 is 0 first to really understand whether this program, to really make this program work. So there are multiple boundary conditions that this programmer was not careful in dealing with. One boundary condition was what the result should have been, and what the result. So I think I see a question: why doesn't it work if R5 is equal to 0? Because you can see that you basically do the addition first, right? You add R2 to R4, and then you R5 becomes -1 over here. So remember, the value of R5 is basically you add R4 to itself. Basically, you get the result 10 if R5 is 0, which you should not get. You should really get 0 because you didn't check the boundary condition at the beginning. Okay, okay. So we discussed the breakpoint. So I went to forward. Okay, so basically a good test should consider the corner cases, meaning unusual values that the programmer might fail to consider. And again, this is not a well-written program because it didn't consider many corner cases, including whether R5 was 0 and whether when you should really branch over here. Okay, so very quickly, let's talk about conditional statements and loops in MIPS assembly, because it's going to be useful in your labs. Again, if you have to go somewhere, feel free to drop off. You can watch this later, or you will learn this anyway in your labs by yourself. But I'm going to cover it relatively quickly so that you have at least, if you want to watch it, you can actually watch it if you cannot attend it right now. But again, you're going to do this in your labs, as I said, so you're going to learn it by hand anyway. And the best way of learning is really by hands-on learning. So in MIPS, we can create conditional constructs with conditional branches, as we discussed. You can do branch if equal, as we discussed. And we're going to see an example of branch if equal. So high-level code looks like this. If I is equal to j, f becomes g plus h. And then independently of that, we subtract I from f. This is what the program looks like. You could call this silly function again, right? And MIPS assembly looks like this, basically. One way of doing this, encoding this in MIPS is, or programming this in MIPS is, basically we branch not equal if S4 and S3. Basically, we check if S3 and S4 are not equal and assume that S3 and S4 contain I and j. And if they're not equal, we skip the add. That's what this instruction says, right? We go to L1, which is the label of the next instruction. So if S3 and S4 are not equal, branch not equal, then go to L1. If they're equal, that means that we're going to do the add. So this is what it is, basically. It's very simple. You compare to two values, and you do a branch if the two values are different. Okay. So if this statement was a little bit different, you had an if and else statement. Now you need to do something a little bit more, right? Basically, we use an unconditional branch to skip the else subtask if the if subtask is the correct one. So what does this mean? Basically, it means this. We write the code like this. This is the corresponding MIPS assembly code to the high-level code. We again have the branch not equal. If S3 is not equal to S4, meaning I is not equal to J, we skip the add and we go to done, essentially. Sorry, in this case, we do the else, right? Yeah, this is a different code. So we basically need to do the else, which is the L1 over here. Because if I is not equal to J, we do F equals F minus I, which is implemented by the subtract instruction. But if this branch condition is not true, we do the add, but we should not do the else. To be able to enable that, we have an unconditional jump. Basically, if we do the add, we should really jump to done and skip the subtract. So hopefully that's clear. To be able to implement if and else statement, you need two branches. One is a conditional branch, and the other is an unconditional jump that skips the else part, right? Conditional branch skips essentially the target that is supposed to be executed if the condition is true, and unconditional jump skips the part that is executed, the subtask that is supposed to be executed if the condition is false. There's a question: can you jump back in the code? Absolutely. You can jump anywhere, basically. As you can have a label over here saying, for example, at the beginning of an earlier loop. You can have a label at the top, for example, and you jump to that. So you can jump anywhere as long as your offsets are fine, basically, as long as you don't violate the offsets. But even then, you need to use a different addressing mode if you want to jump to anywhere in the code, right? Okay, so basically, I already said this. You compare the two values, and if they're different, jump to L1. Otherwise, to execute the else subtask over here, right? This unconditional jump jumps to done after executing the if subtask. Okay, while loop is a little bit more complicated. As in LC3, the conditional branch checks the condition, and the unconditional branch jumps to the beginning of the loop over here. We've seen it in LC3. Now we're going to see it in MIPS. It's going to be very similar, basically. You initialize the power and x value. So here, this loop determines the power of 2 equal to 128, which is a very simple calculation, as you can see. And initially, power is set to 1, x is set to 0. So you need to set those values plus the 128 to compare to. And while loop basically does a branch equal over here, it has a conditional branch to check if the condition is still whole. So you need to check the condition first before entering the loop. Otherwise, you may execute the loop one too many times, right? As we saw earlier in the buggy multiplication example, right? Here, it's not multiplication, but it's really figuring out the power raised to the 2, power of 2, right? Okay, so basically, that's what this branch equal does. And then there's a conditional branch to the beginning of the loop. So we execute the loop once, and then unconditional branch, and then we check the loop exit condition again, whether the power is not equal to 128. So if the power is equal to 128, then we're done. If the power is not equal to 128, we execute an iteration of the loop, multiply power by 2, increment x by 1, and then go to the beginning of the loop and then check if power is equal to 128 again. And you keep doing this until power is equal to 128. Okay. The implementation of the for loop is very similar to the while loop. Essentially, this is another loop that looks that is different. It's a for loop. You can see that you're adding integers from 0 to 10. 10 is not included over here. And essentially, it looks very similar, right? Basically, you set the variables, sum, I, and also you set something to 10 so that you can compare I to 10 at the beginning. If I is equal to 10, you jump out of the loop. If I is not equal to 10, you execute the loop iteration, and then you have an unconditional jump back to the branch equal, right? Essentially the same thing, basically, very similar to the while loop that we saw earlier. Okay, so you could use a for loop by using the set less than, which is a way of setting the registers. This is like condition codes in a little bit, but you set a general purpose register, not a condition code. So we use the set less than for the less than comparison. So let's take a look at this. This is another trick you can use, for example. So basically, you again add the powers of 2 from 1 to 100. That's another loop that does that particular task. And to be able to do that, you initialize sum and I. And then until I is less than 101, you basically find the powers of 2 and like this, and then add it to the sum, right? And to be able to do that, you have some initialization, and then you do the set less than. Basically, this what this set less than does is, okay, I already said this. Set less than is essentially the statement. If the value in register S0 is less than the value in register T0, the destination register gets 1, otherwise it gets 0. Okay, so it's basically this statement implemented with one instruction, right? It looks nice, basically. It's a very high-level statement, if you will. You can directly implement a high-level language statement that looks like this. And then it basically tests the condition and sets it less than. And then you check whether T1 is equal to 0. If T1 is equal to 0, then basically that means that you need to exit the loop, right? If not equal to 0, then you should stay in the loop and do the loop iteration, and then basically check the condition again and again. But you should also execute the set less than and BEQ. In this case, you set less than a register and then check whether that register is equal to 0 or 1 to implement the looping mechanism, right? Another way of implementing. You could have done it in some other way also, clearly. So here we have shift left logical. This is essentially multiplication by 2, right? Multiplying by 2 is the same as shifting left logical in binary by 1. And we don't use a multiply over here because shift left logical is much simpler and faster in hardware. Well, let's go into a little bit more into MIPS. Again, this is going to be very simple to many people who know programming. So you don't really need to study this, if you will, but it's instructive, I think, to look at how the arrays are implemented in MIPS. Accessing an array requires loading the base address into a register, as we have seen earlier. So in memory, the array looks like this. Basically, you have a base register that points to the beginning of the array. And then each array element is a word in this particular case. And then basically each word is in the next word location, which has this byte address, as you can see over here on the left. So in MIPS, this is something we cannot do with a single immediate operation, loading the base register. So what do? We use what we learned earlier, load upper immediate plus or immediate, right? LUI and ORI. We've seen this before. If you want to load this address that we know into a register, let's say S0, we first load the upper immediate 1, 2, 3, 4 to the top 16 bits of the S0 register, and then OR the register with the 16 bits coming from this immediate value, 8,000 over here. And then now you have this address, this base address of array in S0. So now you can see how we can construct an address. This is very similar to LEA, load effective address in LC3, except it's more powerful because now you can load a 32-bit value over here. So let's take a look at how we manipulate arrays. Basically, if you want to manipulate an array, we first load the base address of the array into a register using LUI and ORI. As you can see over here, we're going to assume that that's the base address of the array. Now the base address of the array is in S0, and we're going to use things that we have seen earlier, basically. So if you want to get the element 0, we calculate the address as base address plus offset 0. If you want to load element 1, we calculate the address as base address plus 1 times 4 bytes per word. That's why this offset is 4. And then you can actually do the multiplication, do the store, and then do the multiplication and the store. The multiplication, again, is shift left logical because that's simpler to do than just a multiply operation. Now let's talk about function calls, and this is the last thing that I'm going to talk about, and conventions. It's going to be interesting because assembly is interesting, I think, here. But clearly, we want functions or procedures or modules in a programming language because this enables us to reuse code, and we have frequently accessed code. It makes a program more modular and readable. And functions have arguments and return value or values. So this is one example, right? You have a main function over here that gets executed, and then you have a sum function that gets called that essentially returns the sum of the two arguments that it's given. So let's define something. So calling function is called the caller. So the main function is the caller over here. And the called function in this, so main, as I said, called function is called the callee. So sum function is the callee over here. Okay, so there are a bunch of conventions that people provide when you do assembly programming so that you don't destroy registers unnecessarily, and so that you can actually have much more modular code. If you obey these conventions, this is also called the programming interface, or essentially programming interface to the assembly language for a given architecture. If you follow these conventions, and if everybody follows these conventions, you don't need to save or restore some registers, as we will see. So basically, caller passes arguments, jumps to callee. callee performs the procedure and returns the result to caller. So that's and then returns to the point of the call, basically. Let's take a look at this. But callee must not overwrite registers or memory needed by the caller. And this is really important. If the callee overwrites some registers or memory needed by the caller, when you return back to the caller, too bad. You don't have the registers you need. You don't have the memory you need. So that's why we need conventions, basically. So there are some conventions in MIPS and LC3. And again, these are conventions that you should obey if you want to actually be compatible with the rest of the world. So in MIPS, you can call a function or call a procedure using the jump and link instruction. In LC3, you can use a jump to subroutine, JSR and JSRR. These are different ways of calculating the subroutine address, basically. Or you can return, and you can return from procedure in MIPS using the jump register instruction. In LC3, you can return from subroutine ret instruction over here. And the argument values are supposed to be stored in MIPS in registers A0 through A3. And the return value in MIPS is supposed to be stored in V0. Okay, so that's expectation. And V0 is mapped to some register, as we have seen earlier, that I don't have over here again. So basically, let's take a look at a simple example. This is our high-level code. The main function calls a simple function that just returns. And you have this in main function. So the MIPS assembly looks like this. So what this does is basically you have a jump and link to simple. And then you have the add in the next instruction. So simple, in this case, doesn't contain anything, doesn't do anything, except it returns back, right? To return back, you just use the jump register, register A. So why register A? Because jump and link was a special instruction. Jump and link jumps to simple and saves PC plus 4 in the return address register, which is a special register in the general purpose register file, RA. In assembly, you can assume that after you do a jump and link, the return address, meaning the instruction after jump and link, will be stored in RA in the callee. Okay, so basically that's why you can do jump register RA and then go back to this add instruction that comes right after jump and link. Hopefully that makes sense, right? This makes life easier in programming. Basically now you have programming support, the hardware support or hardware software interface support for function calls in the instruction set architecture, right? In LC3, you have a similar thing. Basically, you have JSR or JSRR that puts the return address in R7. So there's a specific register. RA also has a number, actually. But basically, R7 is the RA in LC3. But it's essentially the same thing. Okay, so there's a very good question. What happens if we call a function from within a function? Don't we overwrite RA then? Absolutely. And then if you do that, the task of the simple function over here, if it calls another function, it has to save RA at that point, basically. And that's why we're going to introduce the concept of stack, for example, in a little bit. So that's a very good question, basically. Somebody needs to save. If you're going to overwrite a register that you're going to need later, or somebody's going to need later, you have to save it in memory and then reload it before it needs to be used. Okay, basically, as I said, jump register RA jumps to address in RA. LC3 simply uses the ret instruction, which is essentially a jump register. But it's a specialized jump register, which basically sets the PC to RA, essentially. Okay, so let's take a look at the high-level code over here. Let's look at a little bit more complicated example. So here, we're looking at a main that's called diff of sums. It does something. Don't worry about it. But you can see what it does, basically. It adds f plus g and subtracts it from 8 plus I. And then it basically returns the result, right? So now this is a little bit more sophisticated function. So what does the main do? Basically, main sets up the arguments. So remember, this is the convention, A0, A1, A2, A3. Basically, it can pass 4 arguments to the function, and then it sets 2, 3, 4, 5, those arguments too. And then it does jump and link to diff of sums. And then diff of sums reads the arguments, assumes that the arguments are in A0, A1, A2, A3. So there's some convention for sure that you need to obey to make this work. And then it subtracts, add, subtract, and then puts the result into V0 and jump register RA, which goes back over here. And then main takes the result and V0 does whatever it needs to do with it, basically, to S0. Okay, so basically we've used the convention. Arguments are stored in A0 through A3, and the return value is stored in V0. Okay, I already said this basically. And the return address is stored in RA again. Okay, so there is a need for a stack for function calls for the reason that we just discussed, actually, based on the question that I received. So if you look over here, the diff of sums looks like this, right? T0, T1, S0. What if the main function was using some of those registers that was used by the diff of sums, right? T0, T1, S0. Well, too bad. You're overwriting them, right? So if you remember over here, we're using T0, T1, S0. And we didn't think about this, right? If the main function was using T0, T1, and S0, diff of sums is overwriting them. But we can fix this problem by using a stack to temporarily store the registers that we're overwriting, and then restore them back after we're done with the function. So the concept of a stack is basically, it's a memory area that's used to save local variables that we operate on temporarily. It's a last in, first out queue. You may have seen this in other programming language courses. The stack pointer is a special register, actually, points to the top of the stack. It goes down in MIPS. It's a convention. Again, all of these things are conventions. Even the naming is convention, right? So it looks like this, basically. So you can push values on the stack, and you can pop values out of stack. So look over here. If you look over here, the stack pointer points to this location, this address. It has this value. Maybe you can push two registers on the stack here that have two values, AA, BB, CC, DD, and 1, 1, 2, 2, 3, 3, 4, 4. Now you added or pushed two values onto the stack. And when you actually start, before you start the function call, you actually say, oh, okay, I'm going to save the temporary registers that I'm going to work on, just to make sure that no one is going to, I don't actually overwrite the calling function's registers, right? And you can push them on the stack. And at the end of your function, you can pop them from the stack and put them back into the registers where they were supposed to be. So here, two words are pushed on the stack. Let's take a look at this example. So we have the same function that we saw earlier. It's writing T0, T1, S0, but we don't know if the calling function uses them. So what we do is basically we allocate space on the stack to store three registers. Basically, we do this to the stack pointer. And then we basically store S0, T0, and T1 to memory locations on the stack. And now we can overwrite, because we stored the old values of S0, T0, and T1. Now we can comfortably overwrite T0, T1, S0, and then compute values based on that, based on whatever we want to do. And at the end, before we do the jump register A, we load back the values that we pushed on the stack into T1, T0, and S0 to the corresponding register. So this is called spilling values on the stack and filling values back from the stack. We're spilling values on the stack because we're using some registers that we don't know if somebody else used that called us. And then before the function returns, we're going to fill the values back into the registers so that the calling function sees the registers as they sent the register file to us. Okay, that's the idea over here. And then we deallocate the stack space, because the stack pointer can also be used by the calling function, basically, right? So stack pointer is a common memory area that's used by all functions. And this is a very general way of saving and restoring registers, as you can see. So the question that was asked earlier, RA, right? Register A, if you're going to overwrite, if you're going to call another function inside diff of sum. So if you're going to call, for example, another function, you'd better save RA on the stack and get back RA after that from the stack when you do that. Again, saving and restoring all registers requires a lot of effort. In MIPS, there's a convention about temporary registers. So actually, we did not need to save temporary registers, assuming everybody obeyed the convention again. There's no need to save the temporary registers, because the convention says temporary registers, the calling function should not expect the values in temporary registers to remain the same after it calls a function. Okay, that's a convention again. These are programming conventions. Okay, so there's a register saving convention that enables us to use temporary registers without worrying about the calling function. But if we're using S0, we'd better save it, because S0 isn't that part. That's not part of that convention. Basically, temporary registers are called non-preserved registers. They are not saved. Thus, they can be overwritten by the function. The function, it's not the function's responsibility to save them, essentially. But registers S0 and S7 are preserved. Or they're called callee saved, which means that it's the function's responsibility to save them, going to overwrite them. That's true for RA as well, by the way. Okay, so now we're done, actually. We covered a lot of interesting concepts. Again, you're going to learn this anyway at some point, but hopefully it's interesting if you stayed. If you didn't stay, that's fine. You can watch it, or if you really need it, you can actually refer to the lectures when you need it from the labs. But essentially, we've covered all these concepts relatively quickly. If there are any burning questions, I'm happy to answer them. Otherwise, we're going to call it a day. I think a lot of the questions are already answered. It looks like a lot of them are answered. Yeah. So can we try assembly coding anywhere? I don't quite understand that question, but certainly you can try assembly coding in a machine, right? If you have a, in the machine that you're going to build in your lab, for example, in the FPGA, you're certainly going to do that. Or you can do it in a simulator, or you can actually do assembly programming in x86 as well, but we don't teach x86. But any machine that enables you to execute machine code, you can do that. And there are more detailed answers that the TAs can give as well. Okay. Okay, I think we're done at this point. I don't see any other questions. Looks like Rahul actually provided a bunch of different links, and we're going to provide those links also on the course website. We should make sure of that. So at this point, we're done. Next week, we're going to start with more detailed microarchitecture, and we're going to actually build up to existing microarchitectures. So until then, have a nice weekend and the early part of the week. Take care, and I'll see you on Thursday.